video, we're going to talk about specific heat capacity. We're going to talk about what the mole is and what molar mass is, as well as Avogadro constant, which are some terms you are probably familiar with in chemistry. We're going to define the specific heat capacity and thermal capacity. And the next video, we're going to do some examples with those two, because these are the first two equations we're seeing in this topic. Okay, so a mole is a rodent that digs holes in the ground and lives underground and has very poor eyesight because it doesn't need it. But for our purposes, a mole is a very useful concept in chemistry. So it's often seen for balancing reaction equations. That's probably where you've seen it. And in physics and thermodynamics, it's also introduced to relate the mass of a gas to the number of particles contained within that gas. So it's a really useful concept for thermodynamics, and we're going to be seeing a lot of it throughout this topic. So the mole specifically is the SI unit for the amount of a substance, okay, which is why it's important for relating to gases, because we want to know how much molecules are contained within a gas. It is defined as the amount of a substance that contains the same number of atoms as 12 grams of the isotope carbon-12. So how many atoms are contained in 12 grams of carbon-12? Well, that is the Avogadro constant, and that is 6.02 times 10 to the 23rd. Avogadro constant is named after the 19th century scientist Amedeo Avogadro, who worked at the University of Turin as a physics professor. And he was the primary contributor to this understanding, back when scientists weren't even sure that atoms and molecules even existed. So a pretty important contribution he made. So keep this in mind throughout the unit, these definitions, because we're going to be seeing a lot of them. Next, we're going to discuss the thermal capacity. Okay, so what is thermal capacity? It's the capacity of an object to be heated, essentially. It's the energy required to raise an object's temperature by 1 degree Kelvin. Okay, so if we want to understand how an object is heated, we use this definition, and there's an equation for it actually, so we can calculate the thermal capacity of an object. And that is C, which is thermal capacity, equals the heat required divided by the change in temperature. Okay, and this has units of joules per Kelvin. Or similarly, joules per degree Celsius. Okay, so essentially, this tells us exactly how much energy is required to heat an object. Now, let's say we have two objects. So we have a very tiny object here, and we have a much larger object right here. And we want to know how much energy it requires to raise the temperature of these two objects. Now, how much energy this object, the smaller object, just because it's smaller, is going to require, regardless of what the properties are, in general, it's going to require a lot less energy than this object, because this object is much larger. Okay, so it's going to require a lot more heat to raise the temperature of this object. Now that's in general. It depends what the substance is. So we may have a substance here that is not very very easily heated, and this object may be very easily heated. So perhaps this object heats much faster. But the thing is, it depends on how much is contained. Okay, so it depends on the number of atoms contained in it. So here we have all these little molecules moving around. They have a much larger space to play around with. It's going to take a lot more to heat them up. Whereas this one, there's just particles everywhere, and it's not going to take as much energy to heat them up. It may not take as much energy. So this is what's known as an extensive property. So an extensive property depends on the amount of a material. So this is dependent on how much there is. So the more mass it contains, this is going to change this number. So we want a more specific definition, one that depends on the material. So we have the specific heat capacity. specific heat capacity is the amount of energy needed to raise the temperature of a mass of 1 kilogram by 1 Kelvin. Okay, so this is a bit more useful because it depends on the material we use. Okay, so the definition of this, so this is lowercase c, thermal capacity is uppercase C, and this equation is Q, so the amount of heat, divided by M delta T. So we have this additional term of the mass, okay? And so the units for this are just going to take that mass into account. So joules, kilogram to the -1, Kelvin to the -1. Or if we want to use degrees Celsius, kilogram to the -1, degrees Celsius to the -1. All right, so if we have these same two objects, I'm going to erase this guy. So we have these same two objects we had before, and we have this large object, okay? The mass that the amount of mass they contain is completely irrelevant. So we could have 3 grams of this material, and we could have 10 kilograms of this material. It doesn't matter. It only depends on the substance. Okay? This one could have a much greater thermal capacity, but it may have a much lower specific heat capacity. So this one may not take a lot of energy to heat up, okay, because it's so small, but per unit mass it might take a ton of energy to heat up. Okay, so mass is irrelevant, so it depends on the structure. Okay, and that means looking at the molecular structure of an object, which is why it helps to know sort of what's going on at an atomic level and a molecular level in substances like water or aluminium, copper, things like that. Okay, now the important thing to note here as well is specific heat capacity does not apply to phase changes. Okay, so if we have, for example, this is an ice cube, by the way. So if we have water basically melting into an ice cube, or if we have an ice cube melting back into water, specific heat capacity just doesn't apply anymore because there's no change in temperature. And we're going to talk about that a bit later, but that's something known as the latent heat. And so, more specifically, it's specific latent heat, because specific means per unit mass. Okay, so that's going to come a bit later, but for now, next up, we're going to do some examples using these equations.